Hi, welcome to this module on the understanding of PWM. During this module, we'll look at the explanation of PWM and how it affects actuators fitted within vehicles. Before we start, have you heard of PWM before? Would you be able to identify a component that would be controlled by PWM? Yes, exactly, well done. It's the motorized throttle valve which is controlled by PWM, as the other components are sensors rather than actuators, and PWM is used to control things that do work. So in terms of work, what do we mean by that? Well, by work, I mean components that actually do something. As a general rule, they'll be controlled by battery voltage rather than 5 volts like sensors tend to be. And they will either move, make a noise, or heat up. So what's PWM got to do with these components? Right, first we need to understand what PWM actually stands for. PWM stands for Pulse Width Modulation. This can be referred to as different names by manufacturers and component suppliers. Terms used as an alternative to PWM would include OCR, or Open Cycle Ratio, CCR, Closed Cycle Ratio, duty, duty cycle, duty factor, or on period. All of these terms are used throughout the industry, but as a whole they mean the same thing, PWM. In terms of what it actually is, it's a way of being able to control current flow through a circuit or component, and this is done for several reasons, which would include current limitation to stop a circuit overheating, motor speed adjustment, solenoid position, motor position, or bulb brightness. So as you can see, PWM is used extensively and is a very versatile method of controlling actuators. Let's have a look in more detail. Here we have a simple circuit containing a 12-volt power supply, a bulb, and a switch controlling the negative side of the bulb. And what we're going to do is measure the voltage directly after the bulb. So with the switch open and the bulb not illuminated, how many volts should be measured? Yeah, exactly. You'll measure 12 volts or whatever the supply voltage is. Since the circuit is not complete, you would measure all of the available pressure or voltage. So if I were to close the switch and thus illuminate the bulb, what voltage would then be measured directly after the bulb? Yeah, exactly, well done. The voltage after the last component in the circuit should always be 0 volts. Okay, so as a little recap, if we have the switch on the negative side of the bulb and then measure the voltage directly after the bulb, with it switched off, we'll see 12 volts. And with it switched on, we'll see 0 volts. It's very important that you understand this basic principle to be able to fully understand PWM. The reason for this is because if the switch was on the positive side of the bulb and then we measured the voltage directly after the switch, we would see the complete opposite thing occur. We would see 12 volts with the bulb on and 0 volts with the bulb off. So let's do this and show you. If we fit the switch to the positive side, we can see 0 volts and the bulb is off. Turn the switch on and we can see 12 volts. Okay, so if we move the switch back to the negative side, as that's where most circuits are controlled on a vehicle, if we switch on the circuit, the bulb illuminates at full brightness. But what if I didn't want the bulb at full brightness? What if I wanted it to be half its available brightness? How could this be achieved? Well, one way would to be using a resistor of the same value as the bulb wired in series. This would be a very good solution if I always wanted the bulb at that brightness. But I may want the bulb perhaps a third as bright, which would mean a different value of resistor. Or I may want the brightness to be truly variable from the bulb, from off right the way through to maximum brightness. Now I could use a variable resistor, but these are bulky, expensive, and tend to rely on some kind of physical input such as a human, to adjust it. Plus, they can wear out. The solution is electronic control via PWM. It's fast, cheap, fully controllable and compact. So imagine having control of the switch and switching it on and off at a set rate. So we'll do this at, say, once a second, i.e. 1 second off and 1 second on. In terms of a percentage, if we are off for the same amount of time as we're on, then we would be at 50% PWM, i.e. the bulb is being switched on for 50% of the total cycle of one off period and one complete on period. If we increase the frequency, i.e. if we switch the bulb on faster, let's say 10 times a second, the PWM duration would still be the same, i.e. 50% on and 50% off. It's just that we're doing it faster. At this rate of switching, we can still see the bulb flashing. So to stop being able to physically see the bulb flash, we need to increase the frequency beyond what can be seen by the human eye. So I'm going to choose a frequency of 100 times a second. So that here we can see the bulb has stopped flashing. If we look at the negative side of the wire on an oscilloscope, we can see that we're still at 50% PWM, as the off period is equal to the on period, and therefore the bulb is half its potential brightness. If I increase the PWM to 75%, you can see the bulb getting brighter. And if I lower the PWM to 25%, you can see the bulb get dimmer. Okay, so now we know how PWM is used to control the brightness or position of a component. Let's concentrate on the measurement. After all, if you are looking at something like an EGR valve or a motorized throttle as an example, you may want to see what the PWM duty is and compare that to the physical position of that actuator. There are a few methods of testing a PWM signal. One way is to use a voltmeter. However, it's not a very accurate method, as a voltmeter will display the average voltage that it's seeing. For instance, if you had a component which is being controlled by 12 volts and 50% PWM, the voltmeter will display 50% of the available voltage, which would be 6 volts as shown here. So you'd need to convert the voltage shown into a percentage yourself. Some multimeters have a duty cycle mode which will display PWM figure for you as shown. By far the best method of testing PWM would be with the use of an oscilloscope, as shown before. So let's have a look and explain how to read it. Here we can see a pattern of a PWM signal. So if the component that we're testing is being negatively switched, is the on period at the top of the pattern or the bottom? Yeah, well done. If a component is negatively switched, then the on period, which is the time that the circuit is complete, would be at the bottom of the pattern. So to work out the PWM duty factor, we need to look at one complete cycle. And this would be a point anywhere on the pattern where the pattern starts to repeat itself again. I tend to make my life easy and choose the bottom edge and the same point as where it's going to be repeated as shown here. If one complete cycle is 10 milliseconds worth of time and the on period is 2.5 milliseconds worth of time, then all we have to do is a simple maths equation. 2.5 milliseconds divided by 10 milliseconds and times by 100 to turn the figure into a percentage equals 25%. So we can say that the PWM of this pattern is at 25%. And if we look at the voltage on a voltmeter, we would see the remaining 75% of 12 volts, which would be 9 volts displayed, as the voltage is spending most of its time in a high state. And remember, the meter displays the average voltage. So you now know what PWM is, how to measure it, and also how to read it. As you can see, PWM is a very important thing to understand as so many things are controlled by it. That completes this module. I hope you found it both informative and useful.